Hello everyone, my name is Hafeez and today I am here to present the topic of dry etching. I have divided my presentation into two main parts. The first one is the introduction to dry etching. In the second part, I will discuss the basics of plasmas and type of dry etching tools. Let's begin with the first part. The first part is covering number one, what is dry etching? Number two, where dry etching is used in the fabrication. Number three, Etch profile control and selectivity definitions, and number four, why use plasma for etching. So what is etching? Etching is the process of removing regions of deposited films or the substrates. There are two fundamental types of etching. Number one is the dry etching, also known as plasma phase etching. Second one is the wet etching, called the liquid phase etching. So here we are covering the important process of dry etching. So what is dry etching? Basically, dry etching is a vapor or gas phase etching, where etchant comes in as a gas and the byproduct leave as a gas. So having a volatile byproduct is essential for dry etching. Below here in the diagram, I have shown the basics of dry etching. So here we have a silicon wafer, and we have the reactant indicating the fluorine coming down to the surface, and the etchant reacting with the surface, and the byproduct in the form of silicon tetrafluoride comes off. So as in this lecture, we are going to limit our discussion to plasma dry etching, which offers more extra etch profile control, which is not available in the wet etching, which uses liquid instead of gas etching. So down here in the diagram, we have an extension. Rather than starting out with the fluorine, we start out with the carbon tetrafluoride, which is very stable gas, and we use plasma to break up this gas into the ions and electrons, which then reacts with this free fluorine, then does the etching like the I showed you before. So where dry etching is used in fabrication? First, it is used for the removal of blanket layer, such as we can use it for removing resist after an etch process or other things. Secondly, and the most importantly, for patterning, in patterning we use mask to block the reactant and the ions, so that we can duplicate a copy of the mask in the material on the surface of our wafer. And usually the mask is often a photoresist. So let's show a diagram of how this works. So here, let's say I start out with a substrate with a uniform film on that substrate, and I put a photoresist layer and a pattern it typically with electron beam, and I want this. Kind of a etching. So what we do is I want to pattern, and the way I get this is I put a photoresist layer and pattern it typically using electron beam. Then I expose it to my plasma etching process that selectively removes the film in the exposed region as shown here. And then I remove the photoresist layer. So now I have a pattern film on my substrate, as you can see here. So these are the steps that I have defined. So now here I want to do some definitions for etch profiles. So typically etch profile is critical to the structures and that we are interested. So for the edge profile, we required a minimum edge loss in case of nanostructures, whereas in case of other structures, we have some slope and maybe a little bit undercut, which is typically because of the step coverage issues. Here, I have shown the case which I am going to define it is the anisotropic etching edge profile. In anisotropic edge profile, we have typically the vertical etching and there is no horizontal etching, and it completely replicates the mask in the film. In the second case, we have an isotropic etching. In this etching, we have undercut. Here we have an undercut which is equal to the edge depth. So here the etching is equal in all directions. So this is very useful etching profile for some structures. So in the last case is the near isotropic and directional edges, in which etches more in vertically than in horizontally. So these are some of the edge profile controls. Now there is another definition which is related to edge selectivity. Edge selectivity is the ratio of the etch rate of the material to be removed divided by the etch rate of the material to remain. So again, in the diagram here I have shown, I have the substrate, the film and the photoresist. So now I have removed some of my photoresist and I am etching this material. The reason why I want selectivity is I don't want to lose this mask material before I get all the way through the film I'm etching. The second reason is when I go all the way through the material and I hit the substrate material, their selectivity can also be very important, such as, for example, if I'm etching a gate over a gate oxide, a thin gate oxide, I have to stop immediately before going through that thin oxide. So therefore, I want a very high selectivity to the material I removed to my underlying gate oxide. So normally we want a high selectivity. So here is an example that I have shown. This is an example of etching of polysilicon over a silicon dioxide. So this is the near anisotropic etch case. Here we have the top layer is the photoresist here, and after that we have a polysilicon, and after that we have silicon dioxide. So here are the selectivity ratios for the polysilicon to the photoresist. We have a selectivity value of 6, and for polysilicon to the oxide layer the selectivity value is 13, which is high. So the selectivity value varies from 1 to hundreds up to 1000 depending upon the process and the details. So now, why use plasma for etching? There are a number of good reasons. First, we can use it for generating local sources. So, like I was saying, I showed etching of the silicon with the free fluorine. Well, free fluorine is very reactive, and it is much easier. And safer to generate the fluorine locally using plasma. Second, plasma etching is often much easier to do than the wet etching. Third, the aspect ratio is very high. We can get very high aspect ratio using plasma etching. What is the aspect ratio? Aspect ratio, here I have shown in the diagram. So the aspect ratio is the ratio of the depth divided by the width. So here I am showing in etch into the silicon with an aspect ratio of 40 to 1. The depth wise we have 40 and in the width wise we have 1. So, and another important thing about the plasma etching is the ions, which can be used to bombard the surface and can do number of useful things like, number one, the ion can clean the surface and remove oxides and polymers before etching. And second one is they can activate chemical reactions like, for example, the radical could sit on the surface and do nothing, and the ions can come and break down the bonds and allow the reactions to proceed. And another good reason to have ions is that we can control the ion energy and the directionality. The ion energy and the directionality are the key for an isotropic etching. Higher energy mean more directional ions and more anisotropic etching. So in this diagram, I have shown the role of the ions and the etching process. So here in the top, we have an electron colliding with the source molecule and generating free radicals. Electron colliding with the source molecule and generating free radicals. Those free radicals then diffuses to the surface, which I want to etch, and it absorbs into the surface. And if it is like a chlorine, it just sits there. But if we have an ions come in, that ion creates sites by breaking bonds, let's say silicon bonds, and when the bonds are broken, the absorbed agent can react with the material and let's say silicon, and then form a volatile product and lead to the chain reaction of the spontaneous reaction that form a volatile product. So here is an example of the reaction of the chlorine. Here I have here we have a chlorine gas going into the plasma. The electrons in the plasma breaking the chlorine gas into two chlorine atoms. Then these two chlorine atoms plus with the ions and plus silicon, they form, they yield silicon dichloride that comes off. So we can either have dichloride or trichloride that come off. If you have a dichloride case, then it can react in the gas phase and give us the more stable form of the silicon, which is the silicon tetrafluoride. So now here we have a summary of the first part of this presentation. Dry etching is a gas phase etching where byproduct totality is essential. Plasma offer a lot of advantages over wet etching. One of the big advantage is the flexibility of the edge profile. We have an isotropic, anisotropic, and near isotropic or directional profiles, and we can control. We can generate local reactants and radicals, and similarly we can control the ion bombardments, which used to activate the surface in addition to the cleaning and to the ions directionality. So that so here we have finished the part one. So next I'm going to uh, talk about the second part of the presentation, which is related to the basic of the plasmas and the type of dry etching tools. So let's start the second part of our presentation. In the second part, we will discuss the basics of plasmas and type of dry etching tools. So this part, we will going to cover the basics of plasmas and the sheet regions, parallel plate configurations, induced coupled plasma configuration, and the downstream configurations. So let's start with the basic of plasmas. Plasma is basically is an ionized gas, which is the which consists of equal number of electrons and ions. It is also known as the fourth state of the matter, which is commonly used for fluorescent lighting. So here in the diagram, I have shown the vacuum chamber. In the vacuum chamber, we have an electrical power. So we are going to limit our discussion to the RF power because we can also, since we can also generate the plasma using DC power, but from etching point of view, plasma etching point of view, DC power can cause damage to the wafers. So we will stick to the RF power. So here we have a gas coming into the chamber, and the gas is coming out of the chamber via pump, and here we have the light coming out, and inside we have a plasma. In plasma we have neutrals, radicals, ions, and electrons. So as we say that the plasma or the steady state process that results after the gas breakdown, the electron gain energy from the applied electric field that is developed due to the RF power applied. So the electron gain energy from the applied field. So the higher the electron energy, these higher electron energy whose collision will have ionization, excitation, and fragmentation of the source gas molecules. So as I said, plasma or the steady state process. After breakdown, in the plasma region, we mainly see the glow. We have the charge balance where the density of the electron is going to be equal to the density of positive ion. And typically in the plasma processing, we talk about the partially ionized gases. So there are less than 1% of the molecule or the atoms in the chamber that are ionized. So it is mainly neutral species. The glow in the chamber is due to the decay of the short lifetime excited species. Their short lifetime is in nanoseconds. So any place in the chamber where we can see the glow, that means there we have electrons that are excited, or electrons are hot. So they are basically breaking down and fragmenting the gas. And when it is dark, that means we don't have any hot electrons. And such plasma typically at 20 millitorr, we are talking about having the neutrals in the range of 10 to power 15 per centimeter cube, and the radical to neutral ratio is from 50% down to the 10%, and whereas the ions to neutral ratio is 10 to the power minus 3 to the range of 10 to power minus 6. So now I'm going to talk about the RF plasmas and the sheet regions. In this diagram here, I have shown the parallel plate type configuration. So one of these electrodes that is grounded, and the opposite electrode is connected to the RF power. After the breakdown of the gas at the equilibrium, what we are going to see is that we are going to have a central glow region, and we have a dark spaces both between the plate of the plasma and between the electrodes. And the reason we develop these dark spaces is the electrons being very small and travel much faster than the ions. So their numbers are 100 times more velocities than the ions. So it means we have a glow region. The first thing that is going to happen is the electrons are going to start streaming out of the this region, and they are going to charge up on the surfaces. So here I am showing the charge here on the two electrodes. As these surfaces charge up, we are going to develop an electric field that can be retarding for electrons. So electrons are going uh, to want to start turning around and going in the opposite direction. So here, so so I am showing here schematically we have a high current of electron that is coming out of the plasma, but most of these electrons are returned back to the plasma and only small amount make it to the surface. But the amount that make it to the surface is going to be balanced by the same amount of ions that make into the surface. So at the surface, the electron current and the ion currents will be equal. So since so the ions gain energy which depends on the voltage across the sheets and the collisions in the sheath region. So at low pressure, we have the less sheath collisions, which means more directional ions and the more ion energy. At the sheets, we have the voltage, which is known as Vs, which depends on the system configuration, applied power, and the pressure. So, so let's talk about the four configuration of the. So here first I want to give an overview of the four configuration, and I will going to discuss in details, more in details in the following slide. So first I want to discuss is the CCP plasma configuration, which is known as capacitive coupled plasma configuration. And this configuration, there are two modes. First one is the plasma mode, where we have the equal number, where we have the equal electrodes, and the RIE modes, where we have one electrode is smaller than the other electrodes. And I will talk about the ICP mode, which is inductive coupled plasma mode. And finally, we will see the downstream plasmas. So, so starting with the CCP plasma mode. So here I am showing the parallel plate where our plasma is placed between those plates, and there is a sheet between both sides of the plasma between the plates. So the plasma is driven by the RF current that is going through the electrodes. So we have the RF supply, their RF current is goes through these electrodes across the sheet region and through the plasma and then out of the other side. And this RF current is what going to keep the plasma going. So the frequency the plasma frequency that is used mostly is the 13.6 megahertz at the wafer. Since the RF current flow determines the sheet voltage, So in the plasma region, the electrons carry the RF current in the plasma region. So there are a lot of mobile electrons that can carry the current in the plasma region, but at the two sheet regions or depletion region, there are not enough electrons to carry this RF current. And so how the RF currents get across this region? By using the displacement current or the capacitive current, the RF current gets across these sheet regions. So how this capacitive current and displacement current develop? So we know that the charge is built up on both side of the electrodes, and the two sides of the and the two plates of the capacitor. The charge on the one side induces the charge on the other side, and we have basically oscillating charge across the capacitor. So let's talk about the sheet region. So we have electrodes here in the sheet regions, and the charge is building up and going away on the metal electrodes. But at the boundary, here in the boundary, we don't have any electrodes. So the way we get our oscillating charge is by this oscillating sheet. So the sheet is oscillating, it depletes into the plasma, and then it undepleted. So the sheet is oscillating up and down, which gave us the charge per unit time and allow the displacement current to flow across the sheet. So here the relationship between the sheet current and the sheet voltage is the sheet current is directly proportional to the RF current densities in the sheet region divided by the electron densities. Since the voltages depend on the current densities, so the area is now critical in changing the sheet voltage. So the higher the area, lower will be the current density and the lower will be the sheet voltage. So we can increase the sheet voltage by decreasing the uh, area of the plate, area of the electrodes. So here by using this relationship between the Vs and the current density, so we can define the two modes, plasma mode and the RIE modes. So by reducing the electrode area increases the Vs or the Orn's energy. The plasma mode, the wafer, the area of the both electrode is same. So we have a lower Vs value. Whereas in RI mode, the wafer on a smaller area powered electrodes has higher voltage as compared to the grounded plate. In the second case, which is the RIE mode, which is also known as reactive ion etching, refers to the case where we have one small electrodes and one large electrode. And typically what we do is we put the wafer on the smaller electrode so that we can then get this large voltage. And with the two electrodes region, we have a large electrode, where we have a large electrode, we have a low RF current density on the one side, and where we have the high RF current density where the electrode is small. So we can get a large voltage on one side. So typically in this case, we can neglect the voltage here in the large electrode. So we can say for the IE case, the bias voltage is equal to the large voltage, which is across the smaller electrode. So let's talk about the limitation of the CCP. And the main limitation of the CCP is that we only have one power supply. What that means is that one power supply can control both plasma density and ion energy. So this has to do with so that means that we have the division of the power. The part of the power goes into generating the plasma, and the part of the power goes into the sheath acceleration, basically giving us the ion energy. So in the CCP mode, we are dividing up the power between the power going into the plasma and the power going into the two sheets. Or in the RIE mode, the power going into the sheets above the wafer and power going into the plasma. So here we will discuss the induced coupled plasma. In this case, we have a vacuum chamber where we have either a ceramic or a glass wall, and we have the RF current going to a coil on the outside of the plasma. And what this does, it induces a toroid of plasma. So we can say that, suppose we can say that 3 to 5 turns on the outside of the plasma, and we have only 1 turn toroid in the center of our plasma. So basically, another name for this configuration is known as transformer coupling. So here we can get a uniform plasma out of it, and separately we can control the ion energy. So induced plasma using inductive or transformer coupling with minimum current, RF current. So when we do this configuration, we don't have a RF current getting across the sheet. So we don't have the depletion region and all that. So we can put power into the plasma without developing a high, what's called the plasma potential. So with multi-turn external coils induces single turn toroid plasma. The plasma diffuses out of the toroid to be uniform above the. So although we have a toroid, a non-uniform plasma in the center, with the right geometry and pressure and all the configuration, we can get a uniform plasma at the wafer. So now I'm going to show what's called the ICP with the high density plasma. In this configuration, we have our ICP and we couple that with the called CCP action. So we are going to add RF bias to the wafer. Here you can see in this diagram, RF bias to the wafer. So we have a second RF bus supply which is used in the CCP mode to control the ion energy. And this allows us to separate the plasma density into the ion energy. This configuration is called high density plasma or HDP configuration. So repeating what I said before, we have a dense toroid of plasma in the center that spread out the wafer. So there are a number of advantages of ICP or HDP mode compared to the CCP is that we can operate one at low pressure, and we can get the separation of plasma density and the energy. So now I will going to talk about the last part, which is the downstream configuration. In downstream configuration, we are having a plasma chamber which is separate from the wafer, where we have no plasma interacting with the wafer. So we are basically having no plasma stop. This allows us to get away from all these things like plasma charging, ion bombardment, and so on. So it's really for reducing damage. The wafer sit out of the plasma chamber and active radical diffuses that have a long lifetime can go from the plasma through the plasma stop and down through the wafer. And we set up the geometry so everything is nice and uniform at the wafer. It eliminates the damage. So there is no ions or electron bombardment, no charging, and no UVs, but we get no edge directionality. It is going to be totally isotropic so far as etching as goes. In the plasma generation method, we can use the CCP method and the microwave. So there are a lot of ways we can generate plasma here. The common applications are the resist polymer stripping and the surface modification. So, okay, for here is the summary for this part. Let's conclude. Plasma are the steady state balance between the generation and loss of ions, electrons, and the reactive radicals. And we have plasma sheet that controls ion bombardments, ion energy, and ion directionality. The ion energy can be controlled by the geometry, system geometry, and we where we do RIE or plasma mode etching, and we can control it by wafer bias in HDP and ICP configuration. The configuration includes CCP, ICP, and the downstream. So that is all from my today's presentation. I hope you have learned a lot of new things. So here are the references, and if you guys have any questions, you can comment me on the link given below. Thank you. Have a nice day.